Hello, guys.
Okay, let's go.
Yeah, so today our talk will be about the introduction and implementation of the basic RAG pipelines, which are the Retrieval-Augmented Generation pipelines. And I will start to share my screen in a moment. Can you see it now?
Yes.
Yes.
Super. So let's start with the basic limitations of the LLMs, which are then will be diminished and solved by the RAG methods. So as a
Could you make your screen smaller because we don't see the whole slide?
I'll try
Something
now.
wrong with slide format. We see it, yes.
Is it okay now?
Yes.
So I've started to talk about the limitations of the usual and basic. Can you see the slides now?
Sure, yes.
Yeah, perfect. So the basic LLM models are prone to the problems that are caused by their training time. For example, when using earlier ChatGPT models like GPT-3 or something like this, we were often to hear that the training data was something like 2021, 2022, and it was limited by the time when the model was trained. So the models which are trained on the data that was obviously present by the time of training, and when users try to get some new insights, for example, about the information that was introduced after the LLM was trained, well, basically users cannot get any kind of this information. So the limitations of the current LLM training pipelines is that they are prone to hallucinations, which are the situations when the LLM tries to generate the text not by the factual representativeness, but by the uh, words themselves. Well, we can remember that LLMs are basically language models, and their main purpose is to generate the text and not to, well, some kind of facts or not to build any logical consequences. They just predict the most possible tokens in the generated text. And, well, some LLMs are prone to generating some good looking but factually incorrect text. There is an example of a DeepSeek model that was limited by its training time, and it cannot give the user any recent information. So this is the problem that we will try to solve. The hallucinations which I was talking about earlier are the occasions when the LLMs produce the words that are grammatically and syntactically correct. They correctly fit into the generated text, but they may represent some absurd or basically infactual information. The the most frequent reasons of the hallucinations are the knowledge gaps of the models because they just fill the knowledge they don't know by something that can be probably there. But of course, models cannot be sure in this. The statistical nature, which I was talking about earlier, of the LLMs, that they are basically statistical machines that try to predict the next token of the text, are is the limitations of the LLMs itself. It means that they are not designed to operate the facts, but they designed to operate the words. And the next reason why we will introduce the RAG pipeline is because that there is no any possibility of external control of the information that comes into the model and which the model uses to ground their answers on. So the possible bad consequences that we will try to solve is the disinformation, which is basically spreading the false content by the language models. This can be the cause of the loss of users' trust. Well, I don't know any users who will trust the model that lies to them, or maybe not intentionally, but just provides any false information. And some ethical and legal risks can be reached, can be introduced when the loss of trust of the disinformation well causes some partners or simply users to quit using your service. And by the way, maybe you saw that some new recent models such as DeepSeek or ChatGPT or basically every other models try to use the internet. They have the function to look up some information in the web, but it cannot be always a good idea because it performs the search as all the people users do. It just Googles some text query, then it gets the answers and it uses these answers to base its question on them, but it is not the it may be not the case that these the search results are can be trusted and are usable to answer. And one of the recent large news topics was that the influencer couple missed the flight after the ChatGPT gave some wrong advice. Well, it happened only because of the uh, hallucinations of the language model the ChatGPT is based on. And users tried to trust the service they use, and they found out that it was a mistake from them. So the strategies that can be used to mitigate and to solve the problem of mistrust that comes from hallucinations is the prompt engineering itself. For example, we can tell the model not to create or not to come up with some random facts just to fill the answer, but we can tell it to for example, warn the user that the model can provide false information. Well, you probably saw this warning when using some language models, especially DeepSeek loves to do it. Well, it shows you the label that the information should not be trusted and it should be checked. The model itself can tell that it has some outdated information and that the user should recheck it by on their own. To solve the hallucinations in some specific domain, we can use the fine-tuning strategy that basically involves the additional training of the model that will then have some additional, for example, domain-specific knowledge, such as medicine or like any other domain-specific knowledge. But the main disadvantage of the fine-tuning method is, well, it is actually quite expensive because it requires some additional hardware, well, a lot of additional hardware. You can check the training costs of the models, and it requires some, specialists who are in their, who are enough competent to and who have enough knowledge and competence to train the language models because it is not the simplest thing to do. And the RAG tries to solve all these problems by injecting the correct information from some trusted database for the LLM model then to use this information to base its answer on it. So the Retrieval-Augmented Generation is a framework that combines the LLM's versatility and the factuality of the knowledge that can be presented in some form of the database or a knowledge base. And it allows the models to have some additional information when replying the user. And the main advantage of it is that the number, well, I mean, the amount and the novelty of the information can be, well, a lot pleasant for users to work with. I mean that we can inject any recent information into the service that user is trying to use to get some insights, and we can inject a lot of useful information and a lot of factually correct information. So let's try to split um, this definition into words and try to explain each of them. So the retrieval is the part when the model searches some external resources such as internet or the knowledge base to find some relevant information about the specific domain that the model is going to answer. Then all the retrieved documents are sent to the model's context for it to have all these pieces of information like in its mind to ground the answer on it. And then the model, having all the retrieved documents, tries to generate the answer to the user's reply using the most factual and new information that was injected into its context. So let's try to explain the diagram of this approach. We will see the path of the information through this pipeline. The first stage in this pipeline is the user who introduces its query to the system, and then we will try to perform a retrieval of the recent and of the most appropriate information from the database. The vector database is a database that can store all the embeddings that you heard about earlier. The embeddings are basically numerical representations of the text. And this database allows the model or allows the pipeline to search through it and find the most semantically near pieces of text, which are called chunks. All the recent chunks of text from this vector database are then injected into the LLM's context and with the custom instructions. For example, we can tell the model that the users, I will just provide you some example for you to understand what we insert into the LLM's context. For example, we tell it, the user's question was, and we tell the user's question. You can see the continuation of this injection. Then you can use the information from the vector database that can be completely trusted. And then we state, for example, top 5 citations from this database or top 5 chunks of text that will then be inserted into the LLM's context to ground its answer on it. And we tell the model, well, this was the user's query. These are the pieces of text that you can use during answering the user's query. And please answer correctly based on the provided chunks. So the model, having all of this in its context, then proceeds to response, and having all the correct, or as we can, as long as we can trust it, correct information continues to generate the response, having a lot of the useful chunks of text in its context, which reduces the hallucinations because now the model does not need to, well, imagine or to create some facts just to fill the gaps because it has it in its context. It reduces the well, it increases the factuality of the response because, well, the model has all the information that it needs to answer correctly, and it can easily generate a response of a higher quality than the basic LM model without this pipeline. So let's proceed to analyzing what the second step is. How do we actually perform a retrieval? To perform a retrieval, we use embeddings, which are the numerical or vector representations of a textual content. Well, all the language models have a lot of layers, as you may know, that the neural networks consist of layers, and the first one of a lot of first layers of the language models are usually those who try to extract some basic information about the words, like its meaning or its its semantic value, and we can chop the model, leaving only its first layers to extract the only the part to use only the part of the model that can, well, generate some semantic value for the words and embed it into numbers. And then we can use these numbers or vectors to then get the semantic knowledge, semantic meaning of the words. As you can see on the graph, there is a, well, cloud of words, I would say it like this, where the words that are semantically near, they are semantically near on this map, on this cloud. For example, the words, I don't see any good examples on this map, but the embedded words like human or man will be semantically near to the words. I know, like plane and shell. And having this semantical similarity, we can conclude that the words human and man have, well, some they are like have synonymical meaning. They are near to each other, and having in mind that we can look up the database to get some semantically synonymical or near words that are placed nearby, we can get the semantically useful results. For example, how the earlier databases and how the well, basically uh, columnar databases work. When we try to search some information in it, they just look for the exact matches of the text. And it can be quite painful to extract the information from them, well, because we need to match the text that's stored in it to extract it. For example, we would like to query one thing, but the chunk of text that in the usual database, yeah, has some different wording, so that our request will fail because the words did not match exactly. And the concept of embeddings and the concept of the vector similarity allows us to get some search results that are based not on the word matches, but by its meaning matches. So, continuing the slide, an embedding is a piece of text that, as I told you, uh, embedding is a piece of vector, is a vector that represents some meaning of the text, and two texts or words or tokens are near on the embeddings space, when they are near in their meaning. So it raises a question that we need to get some insights by looking the most near words or by the most near pieces of text or chunks in the database, and we need some measure to learn the to know the distance of the words in this text or in the database. So we would like to use the cosine similarity, which is from the uh, linear algebra course, which shows the similarity of vectors or of their direction. If two vectors are pointing in the same direction, their cosine similarity is high, and if they're pointing in different direction, their cosine similarity is low. This was the measure of the similarity. Well, let's try to stop on it and get an example for it. As I told you, the cosine similarity measures how two sentences or words or texts are close to each other by comparing their vector representations. And how do we get it? How do we create it? By the, as I told you on the previous slide, by the chopping off, say, the head of the LLM model. Uh, we can then extract the internals, internal data that comes in this model, and use this internal data as embeddings to have some vector representation of the text or of the words and sentences. One key point that I told you previously is that the vectors represent the semantic meaning, or just simply talking the meaning of words. And it is crucial for our task because it allows us to get the most relevant results in our search, not using any word matches or exact matches or some patterns, but only the semantic meaning. And as the context matters for our query, because for our task, because the same word may mean a lot of may have a lot of different meanings uh, when used in different contexts, and the key point of using the LLM model to get the embeddings for the words is that it has a clue about how to embed each word. How to embed each word. I'm sorry. I was talking about the context, and the thing is that even I'm sorry, guys. Uh, try the third time. So, although the tokens or the words might have different meaning in different contexts. Guys, sorry, Timur. I think I need a quick replacement for me for like a minute.
Oh yeah, yeah. Let's make a pause, drink some water, and just come back when you're fine.
Mm-hmm.
Problem.
Yeah,
No
I'm
worries.
okay.
No worries.
So, trying again. The thing I was talking was about the context, as the word might have different meanings in different contexts. We need to know when to use each meaning of the word. And the magic of the embeddings is that they depend on the context of a word and not a single word. And when getting an embedding for example, a text or a sentence, the embeddings have well, the embeddings have all the information that needed to get the right meaning of the word. As we can see by the example, that there are two sentences that have some synonymical, meaning the cat is sleeping on the couch and the animal is resting on the furniture. Well, they are basically rephrased versions of one another. And the similarity score for them will be high by the way it measures. The measure of 1 is the highest similarity, meaning that two pieces of information are exactly the same. But here we can see a high similarity score because all these sentences are synonymically near to each other. They have a lot of common in their meaning, and the vector similarity for them is quite high. So now we found out how to embed the sentences or the chunks, which are the pieces of text, into vectors, and that these vectors can be then used to get the similarity for some pieces of information. And then we can use it, we can kind of exploit it to build a pipeline that can help our AI assistant to have well all the benefits that we were talking about earlier. Now we need to know how to load large pieces of text into the model's context. As you know, language models or LLMs are limited in their context. For example, they can hold a limited number of text, a limited number of words in their context, and well, we need to somehow solve this problem. For example, we want to build an assistant that can well answer the user about the I know like War and Peace citations. As you know, it is a quite large text, and it will not fit into the model's context on its own. So we need to somehow split it. It is the process of splitting a large text into a lot of smaller pieces is called chunking. Chunks are the little pieces of one large text that can then be inserted into model's context to allow the model to use the text, but not to load the whole text into its context. So the main aspects of the chunking methods are the well, you need to think about how to split the text into different chunks because it can have a kind of crucial impact on your system. For example, we can split the text directly. For example, by sentences, we can split the text by the full stop signs so that the chunks will be the separate sentences of the text. But then it raises a problem when the text is not, when the sentence is not, when one sentence is not enough to base our answer on it. So then we need to think how to use a lot of sentences in one chunk. For example, we can split the text by three sentences. Then we probably can mitigate the problem of well, having not enough context by just giving more sentences into the model, but then the next problem arises. The pieces of text when splitting it by full stop signs or by sentences and combining these sentences into, for example, triplets, we'll have a problem of having the right context on the, for example, on the end of one sentence and in the beginning of the another sentence. And we would, ideally, we would like the model to have the end of the last sentence and the beginning of the first sentence of the next chunk loaded both into the context. And then we need to introduce some kind of stride when we not only separate the text by sentences, but we also include the uh, intersection of chunks into the database so that we can try to help the model when the needed information can be combined in the intersection of chunks. And the collection of chunks, when embedded and encoded into vectors and then stored in some kind of database, is usually called a knowledge base. Now we need to know what are the vector databases themselves. Well, you may know about the relational databases. You may know about non-relational databases that have some structure. Well, the relational ones have some structure. They represent tabular data, and non non-SQL databases can have a lot of arbitrary other meanings. But the kind of database that we will need now is a database that is optimized for storing the vectors themselves. Well, because we operate with vectors after embedding all the pieces of text. The main usage of the vector database is to get a lot of text chunks, embed them, and load them into this database because, well, it optimized for the vector queries. For example, it can perform a query like finding a lot of similar vectors well, quite efficiently. So this is an ideal solution for our task because our task is to find a lot of vectors that can be semantically near to the user's query. This database stores all the information as well, vectors themselves as the arrays of numbers, and it can also have some additional metadata stored near each chunk of text. There are a lot of vector databases. The most frequently used are the Chroma and Quadrant databases. Well, they all serve the same purpose of storing the vectors and then extracting them. But the main differences in these databases come from the well, development teams and other additional features that they provide. Because the base, the most frequent case of using the vector database, which is, well, storing and retrieving vectors, is supported by all of these databases. We have talked about the path of the user's query into the retrieval phase, and now we need to know what is the role of the LLM itself in our pipeline. Let's repeat the whole pipeline. So the user asks our system some kind of question. Then the user's query is encoded into vectors, or we can call it is embedded. And then the database searches for example, top 5 texts for top 5 chunks in the database by the cosine similarity with the user's query, so that it will produce the 5 chunks of text that are most semantically near to the user's query. And then we could, well, actually just output all these chunks to the user, but it would be rather a, like Google web search and not an AI thing. So then we would like to form the textual reply to the user's query, which will be grounded on the data from the database. So it is the task of the language model to give the user a coherent and, well, natural reply. We give the LLM the user's query and the chunks that were loaded from the vector database. And the LLM, having all of this in its context and also a system prompt, generates the answer to the user's query based not on its, well, general knowledge that it got during the training phase, but from the vector database that can have some recent or factually correct information. The key point here is that, as you can see, the LLM starts or well, we start to use the LLM only after we got the needed chunks of the text, meaning that the LLM does not perform any kind of search itself, because its primary task is to, well, its only capability is generating text, so that the retrieval and augmentation part is done by us, the developers. Uh, then there are some additional points and additional hacks that we can introduce. I was talking about the naive or basic RAG pipeline. It is the most obvious and easy to understand implementation, having that the user's query is embedded into the vector as it is. Then top k chunks from the database are extracted and given to the LLM that produces a prompt. Oh, that produces the answer based on the on its system prompt, and well, it raises a problem during the retrieval phase. For example, when the user's query can be embedded into a vector, but our database may not have the needed chunks of text that are well, semantically close enough to the user's query. For example, because the user formulates its question in some, I know, like maybe special wording or having using some grammatically unusual sentences. And the problem that we will then solve can be solved by the pre-retrieval phase. The more advanced method of performing the RAG search is when the user query is not embedded into vector and then used for searching the nearest chunks. But when the LLM paraphrases the user's query and rewrites it so that we can get the more relevant examples from the database. For example, if the user's query was, let me come up with some example. Well, it actually can be thought as we Google information online. We have a question, for example, like what is something, and then we do not. Well, it can be possible that we type what is something into the Google search bar, but it is usually enough just to rephrase this query into more simple words. For example, we do not Google what is something, but we just type in the words that we want to, I know, get some definition of. And the key point here is that we tell the model to do this task. We tell the model to paraphrase the user's query so that it looks not more like a question, but more like something that we can then find some relevant information using it from the database. So these were the two methods of the retrieval augmented search. The first one is the naive and kind of easy to understand, and the second one is more difficult, but it can provide the better results for users because of the search or the retrieval phase. And now I would like to show you some code examples of how this pipeline can be implemented. By the way, do you have any questions from the theory part? Okay, now I'm going to proceed to the code. I will go through the Jupyter notebook and well, introduce some commentary for it. The installation of the all the required packages is quite straightforward. And coming to the come to the more important parts. So the most interesting part from the imports are the libraries themselves. We would use the OpenAI API to get an access to the ChatGPT model, and we will use the ChromaDB database to store and to get the vectors from it. We try to load the client by passing it the API key and well, all the other parameters that we know that we need, such as the directory of the Chroma driver and the collection name in the database. By the way, this is the feature of the Chroma database. It allows to store different collections of text. For example, if we want to split our chunks into some domain-specific knowledge, such as the collection of medicine, the collection of engineering, and if we are building some, for example, two different assistants for two different purposes, we can use one Chroma instance to serve them all. And for the embeddings themselves, we will use the OpenAI model that creates the embeddings. They serve it using the API. Now, the most interesting part here is the function that gets the embeddings itself. It needs some text to embed. It also needs the model to use for the embedding. The model we will use is this one from the OpenAI. The retries are implemented for it just to increase its like success rate, and the backoff is for the retries. The main usage of this function would be to create the embeddings for the text, and we use them by calling the API and passing the text that we want to embed and passing the model that we want to use for getting the embeddings. Then the function should return the list of all the embeddings in the text that we passed to it. The logic of for and try except is only for the for improving the success rate. For example, if the function fails for some reason, it then sleeps some time that exponentially increases after each failed attempt, and then tries to do it again by the cycle. Then, after we got some embeddings, we would like to store them in the database. We need to create the client object to connect to our database and pass the settings to it. Well, the Chroma actually can be distributed. It is distributed by the standalone database itself, meaning that we can launch it and it runs itself, and then we connect to it. But for our purposes, which are the demonstration purposes, we can instantiate a client that simply stores the data in the directory that we specified, and it runs the database directly from the Python code. It is not needed to use some additional. We do not need to run an additional server for the database. Then we try to create or get an existing collection. There is a convenience function for it to then store the embeddings into it. As you can see, we will try to store the news into the database because the news are quite recently they update frequently, and their key is the relevance of the news, and we would like to create a pipeline that will base its answer on the news that we have somehow parsed from the internet. And then there is a method, there is a cycle just to embed all the news that we got from the Excel table. Well, for the demonstration purposes here, we're using Excel table spreadsheet to store all the news in it, to store all the text in it. And then we just embed all the news that are in this Excel spreadsheet. We get the uh, batch of the docs, not to overload the API and our ChromaDB. Then we embed all the texts and add them into the Chroma's collection, meaning that we insert them into the database. As you can see, we pass the documents themselves, which are in the text format. We pass the embeddings to the database, which are the vectors, and we also pass some metadata, just as some additional values to be stored in the database. After finishing this cell, we will have the news embedded and stored into our vector database. That will allow us then to perform the reg on them. So let's try to retrieve some of the embedded vectors from the database. We can do it by the get function. We just do it for the sample for you to see. As you can see, there is some array of numbers, which is the truncated version of the embeddings, so that the actual embeddings are loaded and stored in the database, and we successfully extracted them from the database. By the way, as you can see, there are 3,000 dimensions in the vectors, so actually each sentence or each word is translated into 3,000 numbers of floating point numbers according to their semantical meaning, and this process is called the embedding of the texts. So later we would like to we do not like to plot it, but we like then to retrieve the data from the database. Well, we would actually use it after we stored a lot of news in it. We would like then to answer the user's query by getting the related chunks from the database and passing them to the model. The user's query is tell me about main events that happen, but it is not actually the best query we can use. For example, we can add what happened. I know, like in. I want to type in the agriculture area for us to have some more concrete and precise question. We introduce the top K parameter, which is top 10 here, but as I told you during the slides, I told the top 5 K. It is the number of the chunks that will be taken from the vector database and then passed to the model. And then we're stating the model which we would like to use for the embeddings. We would use the large model. So then we are implementing the naive RAG pipeline because we do not do anything related to the paraphrasing or rewriting the user's query. We just directly pass the query into the embeddings function and get the embeddings for the user's query. We get the vectors for it, and then we use the user's query in the vector format to extract the relative chunks from the database. We require the ChromaDB to query our collection to give us the top 10 results that will be semantically similar to the query vector, which is the embedded user's query, and store them into the results list. Then it would be interesting for us to see these top k chunks of the text that were extracted from the database. And as I do not have the text themselves, we then would like to run the generation phase. So we will try to write a system prompt for the model that will make our assistant more precise, and the model will be informated that it will be that it will have some text chunks from the database that it can base its answer on them. We tell it to be an expert analyst, which is a kind of a default part of the prompt. We want it to answer the user's question only. We say only because it may occasionally think that the chunks of text that we pass to it are the some kind of user query, and we want to state it that it should answer only the user's query using the chunks of text that we will put into the model's context. And we also tell it to keep the reply concise for it just to generate not too much text. So to insert all the documents that we retrieved, to insert on the chunks that we retrieved from the database, we just concatenate them using the new line symbols. We state the number of source just for the model to have a kind of structural approach to the citations. For example, for it to be able to reply like the citation 1 says that, the citation 2 says another, and so on. And then we just put all the chunks themselves, all the textual representations of chunks themselves into the model context. By the way, keep in mind that we used the vectors only to perform the semantic search. After we have done it, we pass the text themselves, which are in, like letters to the model. We do not pass any embeddings to the model itself. We use the embeddings only for the retrieval phase. Then we just create a conversation, which you should be familiar with. We create a system prompt for the model that I stated earlier. Then we add the context, which is the text pieces from the database, and we tell the model that firstly we would like to give you the context itself. We would like to give you the relevant pieces of chunks, and then we give the model the question of the user. To answer it, we just simply pass it to the model. And then we perform the call itself on the 4.0 mini model and print the model's answer. By the way, as you can see, it was able to get some insights from the vector database, and it states that there are some major changes. The question probably was, it was about just tell me something major, and it's about the EU-US relationship. So this is the well, RAG, the basic, the naive RAG pipeline that I was talking about earlier in the form of the code. So the main aspects of it, I repeat, will be the uh, phase of generating the knowledge base. When we get a lot of news and insert them into the database after encoding them to vectors. After we encoded the news into vectors and put it in the database, we can use this database then for extraction. We get the user's query, embed it, get the vector representation of the user's query, and perform the database search, the database query, to get the top 10 chunks that match the user's query. Then, after getting the top 10 chunks, we pass them to the language model that was told to use them by this sentence. By the way, the instructions, these are only the simple possible instructions. They can be a lot broadened by just concretizing and giving the model more information about what it should do. And then we add, after each user's query, we insert the relevant pieces of text from the database to the model's context for the model then to generate the answer. So I think that this is the basic introduction to the RAG pipeline. The idea of the RAG pipeline itself is quite promising and is already widely used. For example, in the system that I told you, for example, the system that answers the user's query based on the news, some more interesting examples of using the RAG are, for example, the business or companies' internal knowledge bases. When for example, big tech company has a lot of documentation in it. It has a lot of uh, infrastructural or just some procedural data that all the employees should be aware of. And instead of just opening a lot of books and manually searching from them, it is a widely used idea to build a simple RAG pipeline for it, just for the employees to be able to ask the question in the natural language and get the citations from this knowledge base and to get the concise reply for it. Also, giving you the examples of some RAG pipelines, probably um, the most valuable thing that RAG can introduce is when its knowledge is, for example, some kind of well, I see the questions in the chat. Should be embeddings the same for each retry? Yes, they should, because the retry logic. Yeah, I see that Michael replied, and Michael's reply was was quite okay. Michael correctly got the point that we use the retries here only for the occasion of failing API of the failed API call. For example, when some internet connection was lost during the query, or we got some. Usually it is the connection problems that we try to mitigate by using the replies. One of the question is, what is the technique of making good chunks and further data science is trade-off between making lower? Yeah. The technique of making good chunks is based on the problem that you're trying to solve. Yeah, because there is a trade-off of having a lot of small chunks or having a few large chunks. It actually depends on the problem that you're trying to solve. For example, if the problem is, uh, let me think about an example. We would like to make a system that helps, I know, like attorneys or some law students that would like to get the right citations from some law code of some country, for example. Then the best approach, as I would come up, will be the splitting of the law code by its, I know, like articles of the law, because the article is the unit of law, and the system that will provide the consultations considering some law insights would need to have all this chunk into its context, the whole article into its context to answer the user's query. If I had to develop a system that, for example, just provides the citations from the war and crime book, then I would have more little chunks because probably the user would like to have uh, some 2 or 3 sentences. By the way, the sentences they are quite large themselves, uh, so that the user can, well, enjoy the citation of the text from the book. Then I would have more, but more little chunks of text. There is no kind of rule of thumb in choosing the chunk size, because there is always a trade-off, and well, to get the most user satisfaction, you need to adapt this chunking technique into each use case. I think I answered these questions. By the way, but we did not check whether they fit in the context window. Yeah, actually, the context windows are of the models are quite large, but splitting the database on 100 chunks, I wouldn't say that it is the most efficient technique here, because I would rather stick to the chunk size. For example, splitting the database, having each chunk be like, I know, 100 words or 100 symbols. Well, 100 symbols sounds too short for the chunk, but we should not stick to the number of the chunks that will be in the database, but we should stick to the length of each chunk, and it would generally provide us better results. So, are there any other questions considering our today's topic? Yes, the code, I will share the code. You can examine it after the lecture. But keep in mind that the approach here that is used here is the naive search, is when the user query is directly embedded and translated into vectors. And as you can see, it can cause some, it can, well, actually generate quite uh, good results, but we can improve the quality of results by rephrasing the user's prompt and implementing more advanced techniques. If I share the code, it would be a great exercise for you uh, to upgrade it, not by simply embedding the user's uh, prompt, the user's query, but for example, we can firstly have a prompt to the LLM. We can say something like, I will give you the user's query. You should rephrase it for it to be more. Mhm. Yeah, this is a good question. Uh, I was talking about the possible upgrades. So I told you that we can tell the LLM to have some to rephrase the user's query for the embedding, and then try to find the most relevant articles, not the most relevant chunks, not only by the query itself, but by the um, rephrased version of it. By the way, this is a very good question. Can you give some examples how RAG can be developed in multimodal task? Multimodal task is a task when you um, kind of use different modalities of the information, for example, videos or um, images or sounds. By the way, didn't work with sounds at all, but probably the question is about images or the videos.
Okay, we have some problems with connection. I will reconnect in a couple of minutes. Let's wait for him.
Yeah, I'm sorry, guys. My laptop restarted. So, the last question was about the multimodal task, and here the main problem is that the main difference from our approach is that in our approach we use the language model that works only with the textual data, and it can produce embeddings only for the texts. By the way, newer models are multimodal. For example, something like the Google's Gemini 2.5 or the ChatGPT 4.0 are multimodal, and then they can embed both images and both texts. But as far as I know, they do not share the API methods for the users to be able to get the multimodal embeddings. So we simply need to, there are two approaches. The first approach is to simply change the model to the model that can embed the, for example, images. One of the most popular models that are used for this task is the OpenAI's Clip model. And the second approach is more interesting. We can ask the multimodal LLM to produce some description of the, for example, image that we want to embed. And the description, well, it should be quite precise and broad. And then we embed the textual description of the image itself. And when extracting the data from the vector database, if we found out that the descriptions embeddings match the user's query, so that means that the user's the reply to the user's query should be based on this image. We pass the image to the multimodal model itself. So that's the problem that we solved here is having no option to embed an image by the some closed source models like ChatGPT or Gemini, but we can use some open source models such as Qwen or I've only used Qwen for this task, but I believe there are a lot of like Llama models that can produce the embeddings both for images and for the texts. But the key logic here is the same. We just need to get the embeddings for the information of any modality, and then we use the vectors to get the most appropriate results, and then we give the most appropriate results to the model that generates the answer itself. So this is the common method to approach the task of having multimodal RAG. Uh, there will be no division between modalities because the vectors um, for each language model, if we stick to one language model, for example, to Quen model, it has the same latent space or the same embedding space for both images and for both texts. So there is no need to have any kind of separation of the modalities in the ChromaDB, and we can store all the textual and all the image embeddings in it, and allowing our pipeline to extract all the types of modalities that are needed to answer the user's query. So the answer here is that we do not need any kind of separation in this case. So if we do not have any questions, I think that our lecture can be over. Oh, I see. What are the next steps in React development, do you think? Well, actually, it's a good question, Sergey. Let me think about it. I would say that the next step in React development would be the the overall trend of the latest months, I would say, is to minimize the size of the models. When initially, for example, a year ago, the major goal was to build a general huge model that can answer any question that would be near to the AGI, which is artificial general intelligence. But now when the companies tried to build these huge models, they found out that it is quite expensive. It is quite expensive to inference it, and the latest trend is to not have one huge kind of universal model, but to have a lot of small specialized models. And I think that the next step in React development would be that the smaller and more specialized models or experts will be used in each query. For example, the query would be routed to each expert. Like the expert, if the user's query is in medicine, it will be routed to the expert model in medicine. That will be small but powerful enough to and get the domain knowledge of medicine to answer this question. And it would be the key point here is that it would be relatively easy to inference even on mobile devices, as you can see with the latest Gemma models from Google that can be run on the phones. The graph rug, well, I actually don't see any use cases for it, but I think that there is a possibility that there exists some problem that can be solved by the vector. Not vector, but graph databases. I simply cannot come up with any idea. I know, like querying the metro station scheme or something like this, but I simply cannot imagine any use case for it. Rag for each agent. Yeah, and the key point that I was talking about when I was talking about the specialized model is, yeah, the agentic approach. Well, agent is a model with additional context and maybe instruments that it can use, and it is a smart decision to use some more specialized agentic models that can have the rag as an instrument when the model itself decides when to use the rag and when not to use. By the way, it can be done with the hyped MCP protocol. Because the disadvantage of our current approach is that we insert the results, the search results for the user's query in any prompt, but maybe the model does not need it at all. For example, the question is general, like what is 2 plus 2, and no RAG should be performed for this type of question. And the model itself can then decide when to use the RAG pipeline or not. Yeah, thank you. The questions were good. So I think that if there are no questions, our lecture is over.